Okay, so we're going to discuss unit vectors. And unit vectors, what they are, it means that we're looking at a vector that has only one unit. So this is singular, not plural. So we're going to take and find, if we're given a vector, we're going to find a vector in the same direction that's has a magnitude of equal to 1. So it'll be useful for several things to find a unit vector. So we're going to start by just looking at how do we actually find the unit vector. So a unit vector can be formed from any non-zero vector as follows. So if I have the vector u, we're finding u, which is the unit vector. So if we have our vector v and we divide by the magnitude of v, that will give us our unit vector in the same direction. So that'll give us a unit vector u in the same direction as vector v. So we'll take the vector, we'll divide by its magnitude, and the result would be a vector u that's the same direction, but it's only 1 unit long, has a magnitude of 1. So let's look at an example. All right, so we have our vector v here given in component form. So the first thing we want to do is find the magnitude of this vector. So the magnitude of vector v is equal to the square root of -3 squared plus -4 squared. So when we work that out, that's going to be 9 plus 16 is 25. The square root of 25 is 5. Okay, so that is the magnitude of vector v. So now, if we take vector v and we divide it by its magnitude, which is 5, that would be the same thing as, we don't really write it as divided by 5. We do scalar multiplication. So we're going to write it as a scalar number, 1/5, instead of dividing by 5, right? We can think of this as 1/5 that we're multiplying by. Okay, so we're going to do, because we didn't talk about dividing a vector by anything, but we did talk about multiplying a vector by a scalar. So then when we distribute, we get negative, or not distribute, but we multiply the 1/5 to both components. We get -3/5 and -4/5. And that would be our unit vector. So it goes the same direction as this vector, but it's only 1 unit long. So if we were to look at that geometrically, the original vector, vector v, goes left 3 and down 4. Now in a different color, if we went over 3/5, so left 3/5, so a little bit more than halfway of 1, and then down 4/5, almost 1, like right there, that would be the same direction, and it would only have a unit of a magnitude of 1. And we can check that magnitude on this unit vector, right? So the magnitude of our unit vector, let's call this vector u. The magnitude of u is going to be the square root of -3/5 squared plus -4/5 squared. So that would equal 3 squared is 9, 5 squared is 25, plus 4 squared is 16, 5 squared is 25. I add those together, I get 25 over 25, which is 1. So it checks that the magnitude of this vector is 1, and of course it goes in the same direction. All right, so that's what a unit vector is. You take a second and try to find the unit vector for vector v, 5, -12. All right, welcome back. You should have gotten 5, 13, and -12 over 13. That's the unit vector. Let's talk about now some resultant vectors. Oh, I want to say one last thing about unit vectors, sorry. So remember those famous unit vectors are I and j. That's vector I, that's vector j. So 3i would mean the unit vector I in three times, so times the scalar of 3. And if we looked at what 4j is, that would be the unit vector j times the scalar factor of 4. And if we add those together, we get 3i plus 4j. That would give us this vector. Go over 3i's, go up 4j's. We would get that vector right there. That would be 3i plus 4j, giving us an alternate way to write a vector, an alternate form to write a vector in component form. So we could write a vector as 3i plus 4j, or we can write that same vector as 3, 4. All right? So let's talk about resultant vectors. So a resultant vector is going to be how we're going to solve some of our application problems. A lot of times we're talking about for velocity or distance. Okay, we're going to have some word problems with these and some other things. Force. So the resultant vector will have to do with when we add vectors, essentially, what's the result if we add some forces together. So we're basically adding some forces geometrically like we did in vector voyage. So some things to talk about. We have an apparent velocity. And that apparent velocity, if we're talking about a speed, is relative to, like, let's say it's a boat, like our vector voyage. Apparent velocity was when we drew that vector west 30 or 10 blocks, and we thought, like, that's what we thought we were doing, but then we had to correct for the water or the wind current. So it's like kind of when you swim out from the shore, if like you're on the beach and you swim away from the shore, you think you're swimming straight out, but then you turn around and realize that you've been pushed way far down the beach because of the water current. So the apparent velocity is your feeling that you're swimming straight out. Then there's something called a current velocity if you're in water. And that would have been those correction vectors that we used in our vector voyage. And when you add the apparent velocity and the current velocity, you'll get the resultant velocity. It's adding those two together. You add those two vectors together, you get the resultant velocity. So that vector would be where you actually end up. All right? So a boat's speedometer reads 25 miles per hour, which is relative to the water, and sets course due east, 90 from north. The river is moving 10 miles per hour due north. What is the resultant or the actual velocity of the boat? So the first thing is step one, you want to draw a picture. So we got our boat here. We draw our boat. And our apparent velocity is 25 miles per hour. Maybe we're trying to get across the river. Okay? So we think we're going straight across the river at 25 miles per hour. That's the due east part, right? If the river is moving with a current of 10 miles per hour north, that means the water or the current is going that way, right? So we'll draw a vector. We'll add to our apparent velocity. We'll add our current velocity, the velocity due to current. And the result we get is our actual velocity of the boat. Okay? So what is the actual velocity of the boat? So notice that these numbers are given as well, like we have to write in the numbers. Those are our magnitudes of the vectors, right? So if I find the magnitude of that resultant velocity, that is of that vector, that will be the velocity. So step one is to draw a picture. So now we want to determine the magnitude of the resultant vector once we draw it in. So go back to green here. Step two is to do the magnitude of our resultant vector. I'll just call it R in this case. Should use a lowercase. So it's 25 squared plus 10 squared. That's going to be equal to 5 root 29 when we simplify it. Or about, we kind of want the decimal anyway, about 27 miles per hour. That's the magnitude of that vector. So that's why I was asking you to find the distance as a kind of as a an extension the other day, because we can do this with velocities. If the in our vector voyage, the magnitude represented the distance traveled. In this one, the magnitude represents our speed in miles per hour. So you add your vectors together, you know their speeds because they're given in the problem. You have to then find the magnitude of the resultant vector. Okay? So here's one more example that you can try on your own. So you're going to pause the video here. Try this on your own. Actually, this is the end of the video. Come to class with this one done, please.